So the purpose of this talk is really to set up the discussion. So I want to start talking about stellar streams. I want to talk about what they are, how they form, and then spend a bit of time talking about how we can use them to study dark matter. But I'm not going to go into a lot of details. I want to leave some of that for the discussion session. And so this is really an overview, both observationally and theoretically, where we are. Another thing to note is I've left off there's so many references I could have wedged into this talk to refer to claims that I make and results and whatever. I've left a lot of them out. If you're interested, Anna Bonazza and I recently wrote a review article on stellar streams, and it has a long bibliography, so check that out. And figures I've tried to attribute back to the source. OK, so let's start off with what is a stellar stream. And to get to that, I actually want to do a very brief history lesson and talk about how this whole business started. And it goes back to the early 90s, so that's not that long ago. And so this is a fairly young field. And it all starts really with the discovery of the Sagittarius dwarf galaxy, which was found totally serendipitously by a group, Rodrigo Abada and others, who were doing a survey of stars in the Milky Way bulge, the center of the galaxy. And if you look at the distribution of stellar velocity, and this is stellar color, this is what you sort of expect, a roughly isotropic distribution for stars in the center of the Milky Way bulge. And they noticed this other feature here, which has a different distribution of color, which tells you it's a different stellar population. It also has a sort of smaller velocity dispersion and a mean offset from 0. And this is what then they decided was the discovery of the Sagittarius dwarf galaxy. This was in the 90s, so this is pre-large sky surveys like Sloan Digital Sky Survey, 2MASS, et cetera. So they didn't have uniform imaging over this part of the sky, but they cobbled together a couple different surveys people had done, did some filtering to try to select stars consistent with this color distribution, and these are density contours of stars in that region of the sky. There's a couple times in this talk when you have to put on your astronomer goggles. This is one of those points. This is the Sagittarius dwarf galaxy, which has this very elongated elliptical shape. And they also noted this distribution of stars that kind of sprays out from the dwarf, which was potentially other debris associated with Sagittarius. So why was this exciting? So here's a cartoon of the Milky Way, where the sun is. To scale, this is where the classical satellites of the Milky Way are relative to the Milky Way's disk. So these are things like Draco and Sculptor and Fornax. We've known about these for a while. These are all dwarf galaxies, satellites of the Milky Way. They're all quite far from the Milky Way center, but the discovery of Sagittarius brought one much closer to home. It's really just on the other side of the galactic disk, at the edge of the disk, relative to the sun, which is here. And so right away, Katherine Johnston and David Spergel, Lars Hernquist, realized and noted that this might be an amazing opportunity to study the assembly of galaxy halos and stellar halos around galaxies, because this galaxy is close enough to be influenced by the tidal field of the Milky Way. And so it should be, debris from this thing should form moving groups in the halo of the galaxy, and the discovery of these things would constrain the history and the dynamics and so on. Now, the next decade brought a lot of things into light, and that's really the decade of the digital sky surveys turning on. So these are surveys like Sloan Digital Sky Survey and 2MASS, which were digital sky surveys that provided very uniform and well-calibrated photometry for huge areas on the sky. In the case of 2MASS, the whole sky. And so with that, this is a paper by Steve Majewski. This is the first view of selecting red giant branch stars in the galactic halo associated with, this is the Sagittarius dwarf galaxy here. And what you see, if you again put on your astronomer goggles, are these very long tidal tails arcing out from Sagittarius that wrap over 360 degrees throughout the halo out to very large distances, almost 100 kiloparsecs or so. This was very exciting. People then looked at early imaging data from the Sloan Digital Sky Survey, and it turned out that the early imaging data was around a declination on the sky of 0, and there is a globular cluster in this part of the sky called Palomar 5, And if you do a similar thing, you try to filter stars associated with the cluster, you find these very nice tails that connect back, that emanate from the cluster but connect back to it. And so these were interpreted as a smaller scale version of what's going on over here. So those initial discoveries, Sagittarius, the dwarf galaxy and the stream, Palomar 5, which was a globular cluster we knew about, and the tidal tails and the stream associated with that, that led to a whole industry of filtering stars, taking a photometric survey, filtering stars to try to find things that are very distant, metal poor, which is characteristic of stuff in the galactic halo, and very old. And so that led to discoveries of other structures like this orphan stream, this monoceros ring. And then as more and more surveys came online, like Pan-STARRS, later the Dark Energy Survey, there were just tons of discoveries that I'm not going to talk about in detail of streamy features in the galactic halo. Let's get through all this. Cool. So this really laid the groundwork then for what would come next. But this era was a sort of free-for-all in terms of everyone wanting to find streams, and so they would just apply a filtering technique to photometric data. Most of the discovery was done by eye, so you would run a filter through distance or run a filter, make a plot of the stars that pass that filter on the sky, sort of roll back your chair from your screen, squint a bit, and then maybe say that you found a stream. But there was no real standard for what was required to prove that a stream was real or there. So there's cases like this is PAL 5 actually, where it's fairly dense and it connects back to the cluster, so it's pretty obvious. There's other cases where it's, I don't know, you have to really believe. And then there's the whole business of naming streams, which I'm not going to talk about, but that's a separate amusing story that continues to this day. So really at the time, there were many streams where we didn't know if they were truly tidal debris streams, if they were noise, if they were features caused by variable dust extinction from the Milky Way's foreground, etc. And of course, that all changed in 2018 with the first major data release from the Gaia mission. This is data release 2. That was the first data release that provided very uniform astrometry for almost 1 billion stars throughout the Milky Way. And this provided key information that helps us select stars. Well, first of all, it helps us remove contamination, but it also helps us select stars and streams that are actually co-moving, not just features in stellar density, but features that are moving together through the sky. In the past, while most discovery methods, as I mentioned, were done with photometry and squinting at plots and very by eye, the Gaia era ushered in new opportunities and new methods for searching for streams in a more automated way. And so 2 methods that have been fairly successful at finding many, many streams in the galactic halo. One is called Stream Finder. Another is more recent, Via Machinae. These basically both operate by searching for overdensities of stars relative to the background in phase space rather than just in density on the sky. Just as a visual demonstration of the power of Gaia, this is a region of the sky, my favorite region. It's actually a really big region, but anyway, it's 120 square degrees, or degrees by about 10 degrees on the sky. The top plot just shows all stars that appear in the Gaia catalog cross-matched to a deeper photometric survey. So it's pretty boring. This is just like some random part of the sky looking at the stellar density on average. If you apply a photometric filter to the stars in that part of the sky, which is sort of what people did in the 2000s, you see this linear feature appear. And this is the GD1 stream. This is how it was discovered, just by filtering photometry, just like this. But if you additionally do a pretty coarse selection on Gaia quantities, the proper motions of stars, you go from this fairly noisy view of the stream to being able to select basically individual stars associated with the stream. And this is with a pretty dumb, just a box selection in the Gaia quantities. If you do a better job, if you build a model of the density of streams and try to assign membership probabilities to stars, you can get a much crisper and lower contamination view of these streams. So this is another view of GD1, where now these are stars with membership probabilities consistent with belonging to the stream, and it's much clearer of contamination than any previous method. Another point that I'm not going to talk about in detail, Gaia, this is a subtler point, but Gaia has also made follow-up observations much more efficient. And that might sound boring, but in the past, when we just had photometric data, there's so much Milky Way foreground and background stars that it's very hard to identify stars associated with a stream to then target and observe with a spectroscopic survey. Gaia makes this much more efficient, which means we now have a much better understanding of the chemical compositions and the stellar populations of stars associated with some of these streams. Okay, so after several years of Gaia data, many different groups searching for new streams and drilling down and studying existing streams to better understand their origin, what is the sort of census of the Milky Way streams? We know of over 130 streams around the Milky Way. About 20 of them are associated with remnant globular clusters, so you can trace the debris back to a star cluster, or you can associate it kinematically. We think about 6 of them are fully disrupted globular clusters, so there's no associated star cluster left, it's just fully disrupted. 3 are associated with dwarf galaxies, like Sagittarius, the first one. 7 are consistent with fully disrupted dwarf galaxies, but most of the streams, 90 plus another about 100 stream candidates from those automated search methods, are not well characterized enough to be able to confidently place them into one of those categories. We can guess, but we don't really know. So that means they either have sort of missing distance information or no spectroscopic data, or possibly no detection in Gaia at all, so we're not even sure if they're a real stream. This is a more visual representation of where they are. So this is the Milky Way disk. The sun is here and rotating. This is Sagittarius and the Sagittarius stream. These greenish blobs represent the Magellanic Clouds. And this is, I think, about 70% of the streams that I mentioned before, ones that have good distance information, good enough to plot like this. Some other well-known ones, this is GD1, and this is the orphan stream here. One thing your eye might notice is that they seem to be all located around the sun, and that's indicating an observational bias. This is not a complete census. We don't know of all the streams in the Milky Way, or even within a small radius around the Milky Way. It's dominated by the fact that we need to have a Gaia detection of stars to be able to confidently say that it is a real stream, and that means we're limited to where the sun is. This is another way of looking at that. So this is now an on-sky projection of where the streams are. These are just footprints meant to illustrate the outline of where the stars in these streams are on the sky. And you notice that they tend to avoid the galactic plane. And that's another observational bias, which is that it's harder to find a little feature in stellar density in phase space when you have a very dense background of stars. So we definitely don't have a complete census of streams in the Milky Way. And honestly, I think it's going to be a while before we do. But we still have a large sample now to actually do statistics with. And so that is interesting, though it's not complete. Okay, so that is an overview of the observational state of the sort of population of streams. Any questions before we go on to other details? Good. Okay, so now I want to move on to a lot of work that happened in parallel to many of the observational studies that led to the plots that I showed you before, which was to understand how streams form and how we can use them to study dark matter and other aspects of galaxy assembly. So how do streams form? So if you drop a dwarf galaxy or a star cluster into a larger galaxy like the Milky Way, the stars from the progenitor system, as they orbit, can be tidally stripped from the progenitor system. And so through some internal evolution, stars in the progenitor system might just gain enough energy to then be stripped from the progenitor and become and then start orbiting the host galaxy instead of internally within the progenitor system. That internal evolution can either be driven by two-body relaxation, and it's a slow process, like an evaporative process, or it can be faster if the orbit of the thing goes very deep within the Milky Way, which causes tidal shocks of the system, which can then accelerate and pump out debris as it orbits. So this is a way for stars and dark matter, for the dwarf galaxies, to be stripped from the progenitor by the tidal field of the Milky Way. So another way to think about it is in the context of the restricted three-body problem. So this is effective potential contours. This is the larger thing, the Milky Way. This is the star cluster, the dwarf galaxy. And the sort of characteristic scale for this disruption is what I call the tidal radius, but tidal disruption people call the inverse of this, the tidal radius. Some people call this the Hill radius or the Jacobi radius, whatever. It's related to the mass of the satellite, the smaller thing, over the mass of the larger thing to the 1/3 power, and there's this factor of the orbital radius over here. So that tells you that, well, first of all, that's related to the shocking process I mentioned before. As r gets small, the tidal radius gets small, so it can, even if at your orbital apocenter, your tidal radius is much larger than the size of one of these systems, at pericenter, it might actually be comparable, and that can lead to, this is just hand-wavy, but that can lead to this tidal disruption. What happens really is, through that process of heating stuff inside, stars predominantly leave through one of these Lagrange points, the L1 or L2 Lagrange point, and that's what forms both a stream of stars that lead the progenitor system in orbital frequency and a stream of stars that trail. Those correspond to these two Lagrange points here. So together, we call that the stellar stream, the whole end of one tail to the end of the other. One thing we've realized from doing a lot of simulations is that once the stars are tidally stripped, however that happens, which we can talk about later, it's a long story, but once they're stripped from the progenitor system, they basically evolve as test particles. And so essentially, the dominant physics that is telling us how these streams are forming and spreading out over the sky is just phase mixing. You pull a star out, and then its orbit is slightly different from the orbit of the progenitor, and it phase mixes over time. And we do have a pretty good theoretical understanding of how that phase mixing process works in these regimes. So now I want to talk a bit more in detail about why streams are useful. So I guess in summary, the way streams form is tidal stripping plus phase mixing. Why are streams useful? Because for star clusters at least, that process leads to tidal streams that are dynamically cold. So remember that streams form because the stars that are tidally stripped have a very small spread in differential orbital properties from the progenitor. If they had the same orbit as the progenitor, they wouldn't spread out at all, but they have slightly different orbits from the progenitor system, and that's what causes them to either lead or trail. But those spreads are fairly small because they're set by the characteristic scale that we talked about before, the tidal radius, or the Jacobi radius. And so that spread in orbital energy, fractional energy, say, scales with the progenitor mass with the same mass ratio to the 1/3 power. So if you plug in some typical numbers for a star cluster, the enclosed mass of the Milky Way at typical radii is about 10 to the 11 solar masses. The mass of a typical star cluster that might be disrupting is about 10 to the 5. You find that this energy spread is about 1% for a globular cluster, and it could be up to 10%-ish for a dwarf galaxy. So still quite small. You can also, another way to use this number is the orbital time over this number tells you roughly the time it takes for a stream to wrap in 2 pi. So these are long, for a star cluster, it takes a long time, longer than the age of the universe, for a stream to wrap over the whole sky. But for a dwarf galaxy, it can happen in a few gigayears or so. So this property of streams, that the spread in orbital properties is very small, is what makes them dynamically cold and so useful for studying dark matter. And there's two main ways that they're useful. One is that because streams closely trace the orbit of the progenitor system, just from observing a single snapshot in time, we get information about an orbit. And with an orbit, so from the track of the stream, you can then directly measure the acceleration or the mass enclosed within the Milky Way or a galaxy. So this is just an example of a simulated stream. These are the two tidal tails. The blue line is the orbit of the progenitor system. This is a star cluster-like stream in this case. And notice that the track of the stream is slightly offset, but roughly traces the orbit of the progenitor system. And that is sort of like a holy grail in galactic dynamics. In most cases, we don't know anything about orbits, and that's why there's a book called Binnian-Tremaine, because you have to do lots of other things if you only have a distribution of stars at a single snapshot in time in order to turn that into inferences about the galactic mass distribution. If you have an orbit, it's easy. You just measure the difference in velocity at two places, and then you get a difference in potential at those two places, which tells you about acceleration. So one way that streams are very useful for constraining dark matter is to be able to study the sort of global shape and global properties of the mass distribution of dark matter in galaxies. Another way they're useful is that because they're dynamically cold, they should be very sensitive to things, passing perturbations, or things that might fly by, mass that might change around the area of the stream. And so this is just an analog, right? If you have a very smooth pond and you drop a rock in it, you can see the effect. If you have a very hot distribution of water, or like the bulk stellar halo of the Milky Way, if you have a tiny rock or a tiny dark matter subhalo, you'll never see the effect. One way to see this more quantitatively, but still in a very hand-wavy way, if you turn that energy spread that we mentioned before into a velocity spread, we find that, again, for a star cluster, the typical velocity dispersion of debris in a stellar stream is of order a kilometer per second. So that means things that impart velocity differences on that scale or larger in streams should be detectable in the evolution and the morphology of the streams, the stream debris. So if you compare that to what you get from the impulse approximation of just flying a massive object past a point and asking what delta v velocity kick do you get, well, if you do it for a point mass, it's fairly easy. So if you take a 10 to the 6 solar mass point mass and fly it past another point at about 100 parsecs, which is close but not unreasonable in terms of things passing by one another in the galactic halo, with a typical velocity difference of about 100 kilometers per second, which is, again, a typical velocity in the Milky Way's stellar halo, you find that this velocity kick is around a kilometer per second. So that's 10 to the 6 solar masses, but this is point mass. If you do this for cold dark matter concentration NFW subhalo instead, there's a suppression because you have a mass distribution instead of a point mass. You don't have all of that mass concentrated centrally, and so you lose a factor in the mass, and it scales differently with the mass. But now this velocity kick of order 1 kilometer per second you get from a passing 10 to the 7 solar mass-ish subhalo. So again, this is all very hand-wavy just to show that the order of magnitudes sort of work out in terms of being able to detect low-mass dark matter subhalos that fly by these dynamically cold objects. And sure enough, if you run simulations of stellar streams in a sea of dark matter subhalos, in this case, a population of, I think, 10 to the 6 to 10 to the 10 solar mass subhalos with a very simple distribution drawn from analytic prescriptions to match CDM. This is from Ju Yoon and Catherine Johnston in 2011. This is what the final snapshot of a bunch of different stream simulations look like. And most of them look pretty messed up. They don't look like those smooth stream simulations that I've flashed a couple times before. You have places where there's no stars. You have, where is this? Oh, here. You have areas where there's just a part of the stream folded over on itself or jutting out from the stream, and so on. And so this is exciting, because this means that streams are potentially an avenue towards detecting otherwise invisible dark matter subhalos. I will say, in this case, if you look at the most striking features, like the biggest gaps and the features like this, they're attributable to the most massive subhalos in this case. So it's not like a 10 to the 6th solar mass subhalo is going to produce something like this if it's cold dark matter subhalo. Okay, so conceptually it makes sense, but how can we turn this into actual constraints? Like, how do we develop a method to turn this aspect of streams into constraints on dark matter? And the bottom line is, and this is something that can come up again in the discussion, this is still somewhat of an open question. Like, we don't have an end-to-end pipeline for doing this and delivering dark matter properties. But there's a number of good leads. And so I want to go through a couple of them. One is to look at the statistics of gaps in stellar streams. These are underdensities in the linear density distribution along a stream that you might get after a subhalo has flown through and caused some stars to rearrange along the stream. What generically ends up happening is you form an underdensity as the stream evolves at the location where the subhalo impacted. And so this is interesting because it's a fairly blunt tool. You look for the width, the number of gaps, the widths of them, count them for the streams you have in the Milky Way, and you compare that to the statistics you get given a cold dark matter subhalo population. And if you do that, you find that the typical numbers of gaps that you expect for streams like the GD1 stream that I mentioned earlier, this is a paper by Duncan from a few weeks ago, or for other streams, is typically around 1. And that is, that's good. It's good to have a number, but it's a little pessimal because if it were 10 to the minus 5 or 10 to the 5, and we observed 1 in a stream in the Milky Way, that would be much more constraining. But when you predict 1 and you observe 1 or 2 or 3, the optimist could say everything's cold dark matter and we're good. The pessimist will say, let's now drill into all the systematics and figure out how much they matter. So I think this is still a promising avenue. And this is, again, something I want to bring up in the discussion and hear from Duncan about as well. The hope is that if you do this for maybe all streams, the statistics will work out favorably for constraining dark matter. But no one has shown that yet. So we don't exactly know that that's true. Another promising avenue is very related to gaps and is sort of not a generic thing that happens, but happens when you have very much denser subhalos in existence, as you might have in alternative dark matter scenarios. But if you have a very close impact by a dense object, think of a point mass, for example, or something that's, in this case, 4 times denser than a CDM subhalo, you form a gap, but you also can form features like this, which we sometimes call off-track features because they're off the main track of the stream. For GD1, we call these things spur features. But the point is that they form transient structures that tell us a lot more about the event that caused the formation of this feature than if you just had the gap. And that's because the evolution of a gap is degenerate in many of the properties of the encounter. The formation of a gap of a given width is related to the mass of the perturbation, the relative velocity, the time that it occurred, the impact parameter. Those things are all correlated. But if you have a feature like this, you can often do a much, much better job at constraining the geometry and the properties of the perturbation that caused a feature like this. So this again, this event over here is from a 10 to the 6th solar mass subhalo, but much denser than cold dark matter. But if dark matter can make those things, then or we observe them, then that's a potentially interesting path. How am I doing on time? Does that include the question time? No. Okay, good. Okay. So another avenue. I've organized these in a totally nonsensical way, but anyway, this is another one of the methods that people have proposed. This one is much more of a blunt tool than the other ones that we talked about, because so this is the idea of taking the power spectrum of the linear density of a stream and using that as a metric, or using some summary statistic of the power spectrum as a metric for distinguishing dark matter models. But in this case, what you've done is you've taken your stream and collapsed it into a one-dimensional thing, and then further compressed it into a summary statistic. So you've thrown out a lot of the information, like all of the beautiful structure that we see in the streams. This is an example of a real density distribution of the GD1 stream. So you see that it has these variations, and the green vertical lines are placed at spaced at the maximum power of the power spectrum for computed from this linear density. So you can see that, like,
I don't understand.
Yeah.
Is the power spectrum along the stream?
Correct. Yeah. Of this thing. Yeah. So it's basically telling you like the characteristic scale of fluctuations in the linear density, which in a dark matter, so if streams formed very smoothly and you only had dark matter subhalos, then any variations you saw here, bumps and wiggles in the linear density, would be caused by perturbations from subhalos. So that's the thinking behind this method. And clearly, in streams that we observe, there are very strong variations and semi-periodic variations in the linear density. The problem is many other things can cause these kinds of variations. For one, if you have a stream on an eccentric orbit, not a purely circular orbit in the galaxy, then the way that stars move out into a stream follows epicycles. And those epicycles lead to pile-ups of stars at roughly periodic spacings, which can cause variations very much like this. Other things we'll talk about in a minute, but there's other features that can cause power. So this is a paper from Bonnick and Joe Bovey and other people trying to do this, make this kind of constraint from earlier data from GD1. The black points are data, and blue are simulations where you simulate a stream and put in a bunch of other stuff, like the Milky Way disk, a time-evolving bar, spiral arms, and a few other things, and you ask, what's the distribution of power spectra you get from those simulations? And then they claim that in order to get the power spectrum values we observe, you need to have dark matter subhalos. So that's the sort of idea behind this method, and we can talk about strengths and weaknesses and caveats. I think in the interest of time, I'm going to skip this one, but we can come back to this. In some ways, this is an even blunter tool, but it's just the idea that if you have streams that exist, that are observed, is that constraining on dark matter? Because if you have very dense dark matter, maybe it would cause all of the streams to heat, and you wouldn't actually expect to observe very cold structures in the Milky Way. Okay, so now the messy stuff. There's always messy stuff. And the fact is, this says many, most streams have features that require either very detailed modeling, like fine-tuned models to explain, or we can't explain the features that we see. So here are just a few examples. This is the Sagittarius stream. This is imaging data. And it's been known for a long time that there's a sort of parallel structure to the stream. It's this bit right here, this bit over here, which was originally called the stream bifurcation. And we don't know why it's there. People have proposed models where the Sagittarius galaxy was disky, and maybe the rotation combined with tidal disruption could lead to something like this. But those models don't fully explain. We have a lot of good velocity data for stars along the stream, and they can't reproduce it. There's been a more recent idea that maybe there were two dwarf galaxies, like a binary dwarf galaxy that fell in and they both disrupted. But it's very weird then that this fainter stream appears always on the same side. It's always on top of the brighter Sagittarius stream. There's another idea that maybe it's related to a third body, the infall of the Large Magellanic Cloud, the LMC, into the Milky Way. That's again, not fully explaining the velocity data either. So this is an example how even on the very largest scales, the first stream we knew about that's been studied to death has features that we still can't explain. On smaller scales, there are similar anomalies with some plausible explanations. So this is the Palomar 5 stream that I talked about before. Looking at this stream is a little bit too far to have a lot of Gaia data. So this is actually just from an imaging survey from the dark energy camera. This is the cluster. This is the leading tail. This is the trailing tail. And visually, you probably noticed that the tails are asymmetric, at least at constant density threshold. And this photometric survey is much deeper than Gaia. So we would expect to be able to observe stars here if they were there. So we don't think this is a completeness issue or an issue with the survey itself. It seems that the leading tail from Pal 5 is much shorter at fixed density than the trailing tail, and that is not what models predict. I won't talk about the explanation. There's GD1, which I showed you several times already, which has this spur feature up here and many underdensities along the stream. There's the orphan Chenab stream, so the background density is where the stars are in the stream. The arrows show you the mean velocity of stars at a given location of the stream. So on this side of the stream, the stars are doing what we expect, which is they are moving in the direction that the stream is phase mixing and spreading. On this side of the stream, they're tilting away. And that's related to a story about the perturbation that's being caused by the LMC. And it goes on. I mean, we could talk about many different streams that have these peculiarities. This is another example of a stream like GD1 that has maybe a spur feature or a discontinuity in the track of the stream called Atlas Elika Uma. So is it all dark matter? That is an option. It could be a very funny kind of dark matter. Maybe it has to be very dense in order to explain some of the breaks that we see on very small scales in streams. But we don't know. There's a lot of ongoing work that's trying to understand this. But one thing we do know is there's a lot of other things going on in the background. So there's many other time-dependent things that we've only learned about in the last sort of 10 years that can impact streams. One is, I told you this very cartoonish story about how streams form through evaporation of two-body relaxation for star clusters, and that's bullshit, actually. If you just evaporate stars, you produce very low-density tails that don't explain the very high-density streams that we see. So there's clearly something else going on. The star cluster literature is somehow somewhat decoupled from the streams literature and consider it solved, but there's a lot of things that need to be done to put those two things together to understand how the details of the internal dynamics of star clusters connects to the tidal disruption we see, like Pal 5 I showed you. The tails connect back to the cluster. We should be able to explain what's going on there, at least for that stream. There's also other structures in the Milky Way disk, like the bar, spiral arms. There's other large dwarf galaxies, like the LMC and Sagittarius. Those can come close to streams and cause perturbations. So can we disentangle all of this and actually pull out the signal of dark matter? And that is the question. There's a number of more detailed challenges that I think will lead to that. Observationally, this is inferring the densities of streams, getting better data to help understand the formation of the streams and their progenitor systems. There's also a lot of modeling tasks. For example, to understand if we can decompose the different dynamical phenomena that I briefly went through a slide ago. We need end-to-end simulations of star clusters through galaxy simulations to see what the actual prediction of CDM is. Robin, thankfully, is working on things related to that. And we need more concrete predictions of subhalo properties in alternative dark matter paradigms. Because even for CDM at 10 to the 6 to 10 to the 7 solar masses, we're sort of extrapolating. We don't really know what's going on there. Despite all of that, I'm still optimistic. And that is because we have some amazing new data coming from surveys like VIA, new tools that we're working on, and new simulations that are coming. So I think I'll end there. Summary, I guess, is that stellar streams form from disrupted stellar systems. We know of over 100 of these streams around the Milky Way. These are very useful for mapping the global dark matter distribution around the Milky Way. And also, smaller scale features tell us about smaller dark matter subhalos. And we don't yet have robust methods to turn these features into constraints exactly, but we're close, and there's a lot of stuff being done right now to address that. So I'll end there.
Awesome, thanks for the great talk, Adrian. Questions?
I have a question about, well, I guess you mentioned a little bit, but like, how much can we entangle the effects after the thing gets stripped, or like there's some weirdness of the velocity distribution of the progenitor?
Right. So if it's an isotropic weirdness, it doesn't really matter. But things that can matter are like rotation. So if you have, we don't see strong rotation in most star clusters, but this is more important for dwarf galaxies, we think. And there are, you do expect there to be some residual angular momentum, which will cause asymmetries. That can be simulated, but.
Or like deviations from realization of the initial object, like are these expected, not expected?
Well, I mean, one thing to say is we don't have like a beautiful, perfect model for any stream, period. So there's definitely like things we don't understand, but there's things we don't understand and can shove under the rug. Like, for example, a lot of the things, the isotropic changes to the disruption process don't strongly change the track of the stream. That's sort of like what your eye is drawn to as the mean density of the stream. They mainly affect how stars are sorted along the stream, which is like the density of stars. So it's kind of a complicated answer, but we don't think that for some properties of the streams, we don't think it'll be very sensitive to isotropic changes to the disruption.
Thanks.
Sort of maybe a silly question for some context. It looks like when you were showing some of these like stream simulations that they only really simulate one stream at a time. Do people ever think about simulating multiple streams and seeing if they interact and that can produce some of these features that we're seeing as well?
Yes. Yeah, there's definitely been work on that. The cross-section for, well, if you think the progenitors were like isotropically distributed at the radii that we see now, then the cross-section for interaction between a globular cluster and a stream is fairly low, like a bound globular cluster in another stream. Dwarf galaxies, the cross-section can be bigger for certain streams. Like Sagittarius is thought to have come close to a few of the streams. There's another dwarf galaxy called Segway 1 that seems to have just recently passed through another stream. So that's a different story. But one of the advantages is that we think we have a good enough mass model of the Milky Way that we can assess that sort of over one orbital time. Over many orbits, I wouldn't believe anything. So who knows what happened like more than 500 megayears ago or a gig year. But at least in terms of like recent interactions, we can try to assess that.
Talks. For a given stream, you have you seem to have information both on the number density of stars along the stream and also about their like perpendicular velocity, if I understand correctly.
Yep.
So why people don't try to build a power spectrum out of the the velocities?
You could also do that. So one issue is that what we measure is proper motions, which isn't exactly velocity, and many of the streams are very large on the sky.
Ah, okay.
So you don't really have velocity vectors. If you have distance information and you have spectroscopic follow-up, like we will get from surveys like VIA, then you have all the information you need. But then you have typically the noise is very anisotropic in weird ways. Like distance errors are usually large, but sky position is measured very well. and proper motion errors are usually much larger than line of sight velocity. So it's sort of the error analysis becomes challenging. But you're right, that is something we could do.
You mentioned you can model recent interactions of streams, but that over many orbits it's difficult.
Yeah.
Can you turn it around and say, given what we know about the Milky Way and the tidal field there, can we statistically model the perturbing power of all of the globular clusters and the LMC, et cetera, and compare that against the perturbing power of dark matter subhalos?
Yes, we just need a metric for perturbing power.
Right.
But yes, that would be a project. I don't think that's been done.
Yeah, so my question is, when you think about actually doing the baryonic modeling, how settled is sort of the Milky Way's baryonic structure itself? So, you might be tempted to just model it as like a bulge and a disk,
Right.
but then there are so-called breathing modes that people have talked about for the disk, and a lot of dynamical features I can think about incorporating, gas mass changing over time
Right.
based on star formation.
Yeah.
So how deep are the simulations getting into that, and does it affect the streams? Or
So far, they've been very simplistic. So in order to impact a stream, you have to have like a substantial amount of mass change, and you have to have it change on a time scale that's relevant for the orbital time. Typically, when streams pass through the disk, it happens very quick. Like it's happening with a velocity much larger than the typical velocity of stars in the disk, because they're sort of coming towards pericenter as that's happening. But yes, in detail, that will be an issue. We've looked at it a lot for things like the galactic bar, where you can have resonant effects due to the coupling between the angular momentum and torques from the bar and the orbits of streams, where it can have a huge effect on the density of streams. The breathing modes, I don't think anyone's looked at that, but I think that is like a substantial amount of the Milky Way's disk mass changing over time. I'd have to think about the time scales, whether it would work out, but it's something to look at for sure.